Maxwell's demon has been introduced by Daniel. Doesn't need a great deal of review, but we will go through some of it. Is generally challenges to the second law through the Maxwell's demon has been microscopic on the atomic level, like one other fellow was just asking about there. And on the atomic level, things largely are ignored because it's a reversible regime. On the macroscopic scale, it is not. Now, also as pointed out before, the scientific discipline of thermodynamics is considered to be a closed science. That very little has changed to the fundamentals of it for over 100 years. And what has occurred in recent years is just simply advancements in materials and computational fluid dynamics, such as a gas turbine of how do we keep the thing from melting or fracturing and flying apart, and how can we model it according to computers. But it's still with the old concepts that were developed 100 years ago or more. And within the discipline of thermodynamics, it's largely directed by the first law, the conservation of energy, and the second law, the concept of entropy, that energy increases its randomness, and described definitively as the net change in an isolated system's entropy is 0 or greater than 0. It can be stated a number of different ways. We'll just go through this quickly. Heat flows spontaneously from a hotter to a colder object, but not vice versa. When an isolated system undergoes change, its change in entropy will be 0 or greater than 0. The specific embodiment of this is Carnot's theorem, that a heat engine's efficiency is a function of its maximum and minimum absolute temperatures as a ratio, like we see right down here. The second law of thermodynamics is based upon the kinetic theory of heat, that thermal energy is the random motion and vibration of atoms and molecules. Collisions between these atoms and molecules transfer thermal energy, preserving kinetic energy and momentum. Statistical mechanics models this a little bit further by saying, well, these collisions are particle pair collisions, just two of them coming together, and then they go off in whatever direction they do, preserving the kinetic energy and the momentum. Now, on the atomic scale, these seem to be reversible collisions. They will go all over the place. Nothing's lost. We say they are elastic collisions. But when this is looked at on a larger and larger scale of all these particles together in a larger group, it all gets randomized. And another question over here, how do we rewrite the second law? It will deal with this nature of randomness that is underlying all of this. With any law, you must understand the fundamental principles under which the law was identified. And all laws of physics are nothing more than models of understanding. And as our understanding changes, so does the law. Max Planck, one of the fathers of quantum mechanics, was quoted as saying, "We have no right to assume that any physical laws exist, or, if they have existed up to now, that they will continue to exist in a similar manner." All he meant was our awareness of them, our understanding of them, is what is capable of changing. Now, out of the result of the 2LT as we know it, heat cannot be completely converted into work. An engine's efficiency will always be less than 100%. It's assumed to be universal in scope. And isn't that kind of dangerous to operate something in science with an assumption? But it's there. It's never been, nobody's ever had an opportunity to challenge it. So it's been assumed all the way back from Rudolf Clausius. He said something to the effect, well, from these observations, it's just assumed that the second law is precise. And it's also thought to be absolute in manifestation, such that there are no exceptions whatsoever. It'd be like saying gravity is inviolable. There are no exceptions to it. It is absolute. If that's the case, I wouldn't be able to lift this up. Is this a violation of gravity? But this is how absurd the second law is being treated. The second law, as it's understood, is based upon faulty logic, and we rarely go back to understand where it came from. As with anything in science or in the discipline of logic through philosophy, a conclusion is only true if its premises are true. And a conclusion is limited if one or more of its premises is limited. And what's behind the second law of thermodynamics is the understanding of randomness. And things are not always random. Plus, we also have the basic human understanding that you can get to that the absence of evidence is not evidence that it does not exist. Plus, natural laws always affect each other, precluding absolute manifestation. And this is why laboratory protocols are so difficult to do and do it well so that it really identifies the concept in question, because there always are interferences from other effects, and you want to get those out of the way so the effect in question is all that's left to be identified by the experiment. So what this comes down to is that these laws are competing with each other to outdo each other all the time. And a real good example of this, I ran into it with a civil engineer a number of years ago when we were talking about a municipal water tower and being able to measure the pressure on this water tower. He says, oh, it's by Pascal's principle of equalization of fluid pressure on a municipal reservoir. If you close the vent on top, it's same pressure at top and bottom. I said, no, it is not. There's also the effect of gravity that affects it, and it's going to be a lower pressure up at the top than what you would measure down at the bottom of the standpipe in the municipal water tank. But this is the way people think. They don't. We have simplistic models that we study in school, but these models do not reflect the real world that we are in, and the second law is also here. If it comes to pitting one law against the other, the only one that I would bet on winning in any of these competitive playoffs is that the conservation of energy would win if it was pitted against the second law. And then there are other things. The second law pitted against other ones, well, that other one loses at the expense of the second law. Now, I want to go to some historical perspective here and read you a quote from James Clerk Maxwell about the second law. And it's taken from the text that's quoted here. It is probably impossible to reduce the second law of thermodynamics to a form as axiomatic as that of the first. For we have reason to believe that, though true, its truth is not the same order as that of the first law. The first law is an extension to the theory of heat of the principle of conservation of energy, which can be proved mathematically true if real bodies consist of matter, as per definition, acted on by forces having potentials. The second law relates to that kind of communication of energy which we call work. According to the molecular theory, the only difference between these two kinds of communications of energy is that the motions and displacements which are concerned in the communication of heat are those of molecules and are so numerous, so small individually, and so irregular in their distribution that they quite escape all our methods of observation. Whereas when the motions and displacements are those of visible bodies consisting of great numbers of molecules moving all together, the communication of energy is called work. Hence we have only to suppose our senses sharpened to such a degree that we could trace the motions of molecules as easily as we now trace those of large bodies, and the distinction between work and heat would vanish, for the communication of heat would be seen to be a communication of energy of the same kind as that which we call work. The second law must either be founded on our actual experience in dealing with real bodies, or on the hypothesis that the behavior of bodies consisting of millions of molecules may be deduced from the theory of the encounters of pairs of molecules. By supposing the relative frequency of different kinds of encounters to be distributed according to the laws of probability. The truth of the second law is therefore a statistical, not a mathematical truth, for it depends on the fact that these bodies we deal with consist of millions of molecules, and that we can never get a hold of a single molecules. Another quote from James Joule, known to codify the conservation of energy. But the most convincing proof of the conversion of heat into living force, which he called his word for, or phrase for work, has been derived from my experiments with the electromagnetic engine, a machine composed of magnets and bars of iron set in motion by an electrical battery. I have proved by actual experiment that, in exact proportion to the force with which this machine works, heat is abstracted from the electrical battery. You see, therefore, that living force may be converted into heat, and that heat may be converted into living force or its equivalent attraction through space. All three, therefore, namely heat, living force, and attraction through space, to which I could also add light were it consistent with the scope of this lecture, are mutually convertible into one another. In these conversions, nothing is ever lost. Historically, Joule has been thought of as referring to the conservation of energy, but I point out in this quote that as he starts off with right here at the beginning, the most convincing proof of the conversion of heat into living force was the operation of an electric motor from an electrochemical battery. If that was the most convincing, why wasn't his paddle wheel water experiment of converting mechanical energy into thermal energy of the water more convincing? What he was seeing here was that the electrical nature of the battery, by this equation down here at the bottom, the Gibbs free energy equation here, delta G equals delta H minus T delta S, is what determines spontaneity. And in a battery, the release of energy, the delta G value, which runs the battery, actually entrains ambient environment in the battery itself out of its plates and electrolyte. It is an endothermic reaction, and the battery does get cold, irrespective of resistive losses. And this is what he was talking about. In this system, heat was going right into the electrical system and going into work in the electric motor, and nothing else happened to the heat. That is complete conversion of heat into electricity. Now, there are lots of arguments to the contrary of this. It's not a cycle and all that, and this is not the time to get into these details, but I'm just giving you an introduction that there might be a basis for the second law not being the limitation that we all think it is. Now, here's another presentation of Maxwell's demon. By the way, it was called a demon because, well, a parallel. Werner Heisenberg really hated Paul Dirac's work and called the Dirac equation learned trash. A similar dynamic of hate occurred in here with Lord Kelvin couldn't stand this thought experiment and called this intelligent being to do the sorting of the trap door here, a demon. But here's what happens. Fast and slow particles indicated by the length of the arrows here. We can open the door and the highlighted particle will be allowed through to the other side, and conversely, a slow particle is allowed to pass through in the other direction. But now, let's look at a slow-moving particle is deflected back on the same side, and also from the other side, a fast particle is kept. So you keep doing this ad infinitum for a while, you end up with this result: a collection of cold particles on one, or slow-moving particles on one side, and fast-moving particles on the other. And by the theory of the kinetic theory of heat, you end up with a zone of cold and hot with no work done on the system, because the demon that operated the trap door was doing this on by the principle of reversibility, often used in thermodynamics to understand models, that the trap door was frictionless and massless and so could be moved without any energy. But then there's another case now that the information needed to do the sorting can be totally circumvented, and that's where the Proell effect comes in. The Proell effect is the correct analysis of the non-homogeneous constant volume process with displacement and regeneration. This is the classical analysis of the constant volume process, which appears, by the way, in the Stirling cycle, the only standard, well-known thermodynamic engine cycle that people would be familiar with. It's just a sealed volume of gas. Volume does not change. Heat goes in and out, and the temperature and pressure of the gas changes. And this is the way it is represented entirely. I've never found an exception to this. The heat, Q, equals the mass, M, times the specific heat capacity, C sub V, times the temperature difference, equals delta U, the internal energy change of the gas. Wayne Proell was the first person to correctly identify the complex energy flows that take place within the constant volume process with displacement and regeneration. And this is the text from which I first became familiar with it. Talked with him and said, hey, have you ever done any experiments with this? No, I'm in retirement. I don't have my lab at Standard Oil anymore. He was a career chemist. And so I did some work based on the book, stuff he did in the book, and experimentally verified what he did. Now, this is a graphic depiction of what the Proell effect is like in two forms. The self-refrigeration effect, where we start off with initial conditions with a displacer, confined gas, regenerator with a distributed thermal gradient on it, and air that's, let's say air in this argument here, 50 degrees C, is displaced by the displacer through the regenerator to the cold side. What we end up with down here is the bulk gas temperature is below the ambient temperature that we started off with in the system, 20 degrees C. Conversely, the self-heating process, where we start off with gas in the cold side and displace it to the hot side, we end up with a gas temperature that's higher than the maximum temperature of the regenerator. Compression and expansion work take place in the system here in order for this to take place. As gas is displaced, so let's go back to here. Hot stuff is displaced through the regenerator, cooled off. The specific volume of the gas decreases, but this is a constant volume environment. Therefore, the gas on both sides of the displacer must expand to compensate. And that's pressure volume work that is sourced out here and put into the regenerator as extra heat. And what we end up with is the change in internal energy of the gas U plus this work equates to the mass times the heat capacity of constant pressure times the temperature, which is equivalent of the enthalpy change, delta H. All sorts of things open up here, and the ratio of Cp to Cv is the heat capacity ratio of the gas, which is substantial, and there can be a considerable amount of power in here. The implications are profound. The second law can be circumvented. And the Proell effect does this without sorting any particles. All particles undergo this energy transformation. Now, the second law does not apply when heat can transfer elastically according to the kinetic theory of heat across greater distances between particles than statistically allowed for single particle collisions. When the vectored heat transfer via work occurs over distances greater than the mean free path of the gas, the randomness requirement of the second law is gone. And this is how the second law is violated, so to speak. We've put a limit on it, saying it no longer applies, like the limits on Newtonian mechanics. Here's a graphic depiction of transfer of work over an area greater than the mean free path from cold particles to hot particles, sending heat in the reverse direction, which is negentropic. And here's a device which is on display in the back, and I'll have a chance to demonstrate it to anyone who wants to see it with what's left of the conference. Schematic view of what's here of a displacer inside a tube. And this is the way it was built, with steel wool inside of an acrylic cylinder and a bar magnet on top for coupling through the hermetic seal. Thermocouple for sensing, 50 gauge, 1/1000th of an inch in diameter, so it'll show fast response. Ambient conditions, thermal equilibrium, stroking of the device and see what little changes occur in the change in temperature with the thermocouples. This is what occurs when the volume is closed off and it's no longer under constant pressure. And I lift it up, stroking it to the cold side. We get a self-refrigeration spike. I drop it back down, self-heating, and we get this over here. Increase it to from air to argon, and then from down to a triatomic gas, carbon dioxide, and it follows the predictions. You'll see this in the back room, and I did some other embodiments of the tester, and with numerous thermocouples. I now have a U.S. patent issued on a perpetual motion machine. I told my lawyer, have fun storming the castle, and we got it through, because they believed I gave them the science, and it's there. Okay, there are a number of engine cycles have been developed out of this, and I want to show you some pictures before my time runs out. There are mathematical proofs on this. I'd love to show this to anyone and see what they can try to shoot it down with. And this is what a cycle can look like, and we'll talk about this afterwards for anyone who's interested. Prototype was built in 2001, actually a couple versions of them, a Stirling-like piston and displacer mechanism. And I don't have time to talk about it right now, but I'll just give you some eye candy here of a year's worth of experimentation, and I ran into mechanical engineering problems of imperfect piston seals, too much friction in the mechanical linkage, and design issues with the regenerator. Use liquid nitrogen to generate the initial temperature gradient on it, and here's some frost in the Dewar flask at the bottom. Instrumented the living daylights out of it, so I have lots of documentation of it, and this is key. Pressure sensor of the cycle, starting from thermal equilibrium or mechanical equilibrium over here, and then the baseline drift shows the piston leak. But expanding this out, I have the constant pressure process, the constant volume cooling, and constant entropy compression showing up in here. It is working. It just did not have enough energy generated to overcome its internal frictions and losses. Engineering drawing of profile view semi-X-ray through it and view of the flywheel, and I'm out of time, but we can talk later.
We do have a few moments for questions.
Did you ever measure the effect of intention on your experiments?
No,
What would happen if you did?
I don't know. I don't expect there to be any influence there. I don't think this is an area of science outside of what we've normally seen that requires any consciousness intervention. In detail, the science is there, and if you don't see it yet, we can talk more about it later, and it should just be self-evident that it's a natural spontaneous reorganization process. It's not truly spontaneous, it's quasi-spontaneous, that a perturbation of the system must be put in, and that actual energy input is heading towards the natural expression of the second law, but it's less than Carnot if it's done right.
We don't have time to go into detail here, but I just want to stand up as a defender of the second law of thermodynamics.
All right, we can talk later.
Just because it's statistical doesn't mean that we can throw it out. In other words, just because it's not mathematically provable, it still can be very solid. For example, if you take a box of marbles and you put some black marbles on one side of a shoebox and white marbles on the other side, you shake the thing, the marbles will be distributed.
That's right.
That's just statistical, but they really will be distributed. And if you end up doing it with 1,000,000 marbles, they're going to be very, very well distributed.
That's right.
And that concept of mixing is behind the justification for the second law of thermodynamics. And I believe it is solid. Again, I'm not saying enough to argue with right here. We will have a discussion tonight. There's going to be a panel discussion on energy. And I'm hoping that we'll get into some of these issues.
Yeah.
And it looks like I'm going to be the conservative member on the panel, I think. So I'm not sure what will happen with Daniel and several of us this evening at 7:30.
Regional debate is welcome, and actually that's what science needs more of because it's been closed. All I can say to that is science is done in the details. Examine the details.
I guess I wasn't clear if you're talking about potential motion machine, perpetual motion machine. How long have you run any experiment with a net energy output?
I do not have anything with a net energy output at this point. It is only a tabletop physics experiment of the only questionable process in the cycle that is not classically understood exactly as the understanding is. These photographs you saw here were from 2001 when I had a contract with an investor from France where we formed a company called Cool Engines Incorporated. Contract called for $1 million, and in the course of a year to be invested in it, and an infusion of $50,000 was given midway through the year. And when we were ready for the second stage of investment, 9/11 happened, and the investor lost 20% of his net worth in 2 days. And unfortunately, I was funded by his play money, and I never got any more. So that's why it never went any further. But I learned a lot with that, the first 2 prototypes you saw photographs of. Next.
Yes. You say that at the molecular level, things are reversible.
That's right.
Okay, and we're thinking of the second law. Then it doesn't apply at the molecular level.
That's right.
And yet
You may not see a separation on the atomic level, but tiny little ones in space and time have been reported,
okay,
which
now,
just go away.
If you go to the macroscopic level, then the second law applies.
Yes.
Isn't there an inconsistency? What happens? There's some transition point where it doesn't work and where it does work.
The second law is based upon random collisions and departures of trajectories that only conserve their kinetic energy and their momentum from the collision. But that, on a larger scale, as many of them are colliding, ends up being a statistical randomness that's just overwhelmingly impossible to, from a practical point of view, to get to. Like the box of marbles. You can have 5 black and 5 red marbles and juggle them around, and if you do that for 30 hours, you might say, oh, look, they're separated again, and then they're back again. The more the numbers go up, the probability of that coming back to the original state just falls through the floor abysmally. But in this case, as I'm saying, there is no sorting of Maxwell's demon going on, and everything goes through there, and it can ratchet uphill, and you can capture it. I have compact discs here with publicly available computer files, including 2 mathematical proofs. I encourage any of you to take this and study it. And for the skeptics, find the flaws in the mathematical proofs. It's 2 traceable state variables of published gases. Point out the flaws. There's the
Ken,
challenge.
thanks for your nice talk. I sense in the general scientific community, and maybe you do too, but there seems to be a feeling that whatever is true for the ideal gas must be true for everything else, and it simply is not that way.
Well, yes. Now, I don't argue about the ideal gas and the ideal gas law not reflecting that. I see that this kind of process can work with ideal gases or quasi-ideal gases or things that are very far off, close to the critical point of a gas, where all bets are off on the modeling of flow